Why, hello there. I am Sheena's Potato, and welcome to my YouTube channel. Now, you may be wondering who I am, why I am, and what exactly I'm doing here. And that I have an answer for you. I am an individual with a very deep and passionate passion for science, specifically the science of physics, more specifically the science of particle physics. Why? Because I enjoy math. Now, does that make me a nerd? No. Well, yes, but actually no, because the math that I like is cool. Now, what exactly does any of this have to do with my theory? Well, I'm glad you asked. This is my theory. Only there are a couple of things, including my final equation, a proof that leads up to that equation, and some base equations as reference. But what exactly do any of the funny numbers over here actually mean? And to that, I have an answer for you. Now, there are a couple of equations up here that are fairly significant, such as this one representing the velocity of an electron, this one representing the value of a single coulomb, this one representing the value of epsilon null, also known as vacuum permittivity, and this one representing the mass of a single electron in kilograms. Why kilograms? Great question. But what's more important than understanding those base equations is understanding what the actual theory itself is about. And for that, you need to understand ion thrusters. Now, in an ion thruster, there's an anode and a cathode, and electrons flow from that anode to that cathode. And throughout their journey, they'll encounter molecules. They'll bump into atoms in that molecules, ionize them, they become ions, they gain charge, and they'll be attracted to the electric field of the cathode. Molecules are pulled in, and they're accelerated forward. Now, in some cases, the electron from the ionized atoms will be taken off, pulled back to the cathode, and brought back to whatever power source it came from. But in all cases, the molecule accelerates forward and generates thrust. Now, here comes the fun part, my theory. You see, in an ion thruster, those ions already accelerate exponentially towards the cathode due to something called the inverse square law. But in my theory, the idea is that if that molecule enters the ion thruster already in motion, it'll accelerate exponentially faster and exit exponentially faster than it would have if it had close to no velocity at all when it entered the ion thruster. Now, add on multiple phases and accelerate and accelerate and accelerate those ions, you could potentially get them to a point where they're moving close to the speed of light, probably somewhere around like 90%. But if you have all of those ions, all of that intense mass moving close to the speed of light, accelerating as thrust out of a ship, then whatever ship that rocket's strapped onto is going to move pretty damn fast. And that's the gist of it. But without further ado, let's move on to a little demonstration. So I called up the finest Chinese sweatshop on the market to order some electronics components, only to find out they cost $12 for a pack of 3. Thankfully, I have other means of obtaining it. So I set off in search of the part that I needed, only to discover a man on the side of the road who possessed it. I then very kindly asked for the part. He was reluctant at first, but thankfully I convinced him. I then took the part and set off on my way. But what exactly is this thing that I legally obtained? Well, this is a high voltage transformer, and it's a part that I'm going to need if I want to build a model ion thruster. But that begs a question. What exactly is a high voltage transformer? You see, in a transformer specifically made for outputting high voltage, there's a fairly large output coil wrapped around a much smaller input coil. And with an input of very high amperage but low voltage, you'll get an output of high voltage but fairly low amperage. And that's essentially what a high voltage transformer is. But that then brings us to another question. What exactly is voltage and amperage? And that's a great question to ask. Voltage is essentially the measure of how much energy an electron has, and amperage is the measure of how many electrons are actually present. But of course, there are other power units too, such as wattage, which is sort of like the total power draw overall, and other units such as coulombs, which you may remember I mentioned earlier, and 1 coulomb is essentially the amount of electrons present in a given area per ampere per second, which sounds complicated, but really isn't. Coulombs are especially important in ion thrusters because if you know how many electrons are present, you know how many ions can be formed. More ions means more mass exiting the ion thruster, and more mass exiting means more thrust. Now, voltage is also important because if you know the voltage, you know how much energy can actually be exerted onto those ions and how quickly they're going to accelerate because of that. So more voltage means faster ions, which means more thrust, which is good. But of course, there are many other variables that are involved in ion thrusters, but voltage and amperage are the two big ones that you need to know. But with that, let's move on to the next one. So I gathered all the pieces together to assemble the ion cluster, and bit by bit I slowly put together. It was a generally simple blueprint, so it didn't take too long, but after calibrating everything and making sure it was all positioned correctly, it was good to go. So here it is, our ion thruster. It's a fairly simple model, but it's an ion thruster nonetheless. We have our anode, our cathode, our high voltage transformer, and our high amperage power source, which is really just 10 AA's strapped together. It's a little underwhelming, but it works. Now, the anode and the cathode are going to create an electric field. The electric fields are going to touch. Electrons are going to flow from the anode to the cathode, ionize the air in between. It's going to be, anode's going to repel them, cathode's going to attract them, and the ions will pass through a little hole in the cathode and accelerate out forward. Fairly simple. So I'm going to dim the light over here so that you can see the arc better, and I'm going to place my thumb with this little piece of tape out by the exit of the ion thruster. So when the ions fly out, they'll hit the tape and they'll fly back to signalize that it actually is generating thrust. Now, without further ado, let's actually activate the ion thruster itself. You can actually see the piece of tape fly back, and you can see it moving from the ions hitting it, as a direct representation that thrust is being generated. If I deactivate it, you can see the tape fall back into place. Now, this is a fairly small model that doesn't generate very much thrust at all, but it does generate thrust. Now, but this is just an ion thruster. My theory is that if a molecule enters already in motion, then it'll accelerate exponentially faster than it would have if it had close to no velocity initially, which is where the next part comes in. This is a small air pump, and I'm going to use it to generate some form of airflow moving across the anode and cathode to see if the air really does accelerate exponentially faster. So, here you see I have this tube hooked up to the air pump, which will be pumping air across the anode and the cathode while it's running, and if everything goes according to plan, then hopefully I should feel a significant difference in the output of the ion thruster when I put the tape in front of it. So, without further ado, let's activate the ion thruster. So upon activating it, you can see the tape moving again, but now we're going to activate the air pump. It's hard to see, but you can definitely feel a difference. You can feel the ions hitting a lot harder. For example, if I deactivate the ion thruster, and then I position the tape in about the same distance away as it was in the ion thruster from the air pump hose, and activate that, you can definitely feel a major difference. I can barely feel anything here compared to when I can definitely feel it while it was interfering with the ion thruster. So overall, these are all good results. So with everything said, that then begs the final question. Is any of this actually correct? And to that I say, as much as I'd like to say that my theory is 100% perfectly correct, I simply can't do that, just because I don't have enough evidence to fully confirm it. Now, while the math seems to check out, and the results of the experiment seem to prove me correct, in reality, I just don't have the materials and proper evidence to fully prove if my theory is right or not. While I am fairly confident that I am correct, I simply can't prove it 100%, because I just don't have the stuff that I need to do that properly. I do hope that eventually I will be able to get the materials that I need to properly build an ion thruster and measure the outputs of that ion thruster, but until I can do that, this will simply just remain a theory. Maybe I could potentially prove it correct through more math, but without proper testing, there's really no way to confirm it 100%. Despite this, I would like to do a follow-up video where I go into more detail on the funny numbers behind me. And that's really about it. So, am I correct? Great question. Maybe one day I'll find out. And that's pretty much it.